Well, hello. Let's go ahead and get started. Those of you who were at my live test review know that it was kind of a crazy night. I had issues at home with my internet, then I had to go to town. And then I forgot to hit record, so I'm going to do this again with you guys just for recording purposes. Okay, so on your screen, you should be able to see right now what I see on my smartboard. It says Test A, so this is one version of the test that I could have picked to give you. All right, just like we've talked about in the past, if your directions tell you to write something as a power, it doesn't mean to solve it. It means to simply write the repeated multiplication problem as a power. So you need a base number, which is the number being repeated, and then 1, 2, 3, 4, 5, 6, and then an exponent telling you how many times that base number is repeated. So the answer for number 1 is going to be 5 to the 6th power. You do not have to do the whole multiplication problem out. Just write it as a power. However, number 2 says, find the value of 2 squared, or 2 to the second, or not 2 squared, 7 squared. So that means we do have to find the value. So we have to do the math for 7 times 7. And of course, that's going to be 49. Okay. The third question says, determine whether 11 is a perfect square. All right, I'm going to look at my multiplication chart in my math notebook diagonally to see if any of those numbers are 111. Remember, that's a great place to look for perfect squares. And perfect squares just mean that the number is a product of a number times its very own self. And of course, when you look, you're going to see that 111 is not a perfect square. Okay? Now, the next thing we're going to do is we're going to find out what the answer is to this PEMDAS question. All right. Remember to follow PEMDAS. That means take care of what's in parentheses first. And please show your work. Notice how there is no symbol, multiply, divide, add, subtract, there's nothing there. And we revert back, right, to multiplication if there's no symbol there next to parentheses with a number next to it. Now, we can do 15 plus 1 because it is in parentheses, and that is 16. Okay, that's the first step. I got that taken care of. Now, the next thing I can take care of is my squared number here. 4 squared is 16. Okay, I've got that taken care of. Now I have to take care of any multiplying and dividing as it shows up in the problem from left to right. So 9 times 16. 9 times 16 is, I should remember this, I just did this. 9 times 1 is 9, plus 5 more is, oh yeah, that's right. Okay. Now, I know that 9 times 16 is 144, but just in case, we can double check. 144 divided by 16, my answer should be 9 because this multiplication problem just said that 6 times 9. Okay, so, well, let's do it. Shocker. Okay, so now I have 10 minus 9, and my answer is 1. Okay, notice how I've showed all my steps of PEMDAS. I multiplied and divided from left to right as they appeared in the problem, and then I got my answer. Okay? When you're asked to list all the factor pairs, that means every set of numbers, every pair of numbers that builds that number, whole number. Okay, so you could do 1 times 78 to build a 78. You could do, since it's even, I know you can do 2 times something to get 78. And I don't quite remember what that is, so I'm going to need to divide it out. Ooh, it's 2 times 39. Okay, well, is that number divisible by 3? 7 plus 8 is 15, so I know I can divide it by 3. Okay. Nice. So it's divisible by 2 and by 3, so I wonder if it's then divisible by 6. Let's check. Whatever it is. So 6 times 13. And there are no other factor pairs that I can think of for that number. It's not divisible by 7, it's not divisible by 8 or 9, 10, 11, 12. So I think that's all we've got, okay? The next thing is write the prime factorization. Right here is your key. That means prime factors is all I want, so I need a factor tree. So on this one, I could say, well, that one I definitely see is divisible by 4. 4 will go into 12 3 times, 4 will go into 4 once, okay? And 31 is prime, so I can circle him. Okay. So if I'm writing that as a answer, I would write 2 times 2 times 31, right? I could write it 2 different ways, actually. I could write it 2 times 31, or I could write it with a power, 2 squared times 31. Okay? If that makes sense. Ooh, goodness. I didn't erase the answers for the rest of them. Okay, find the greatest common factor of 20 and 80. Well, for greatest common factor, we know that we need to find the factors they have in common. So for prime factors, we're going to just go ahead and do factor trees. With 8, I'm just going to do 2 times 2 times 2. With 10, I'm going to do 2 times 5. Okay, then I'm going to look back at my problem. Greatest common factor means they have to match up. Okay, so there's definitely one set of 2s, definitely another set of 2s, and then a 5 that they have in common. So what is 2 times 2 times 5? Well, 2 times 2 is 4, and 4 times 5 is 20. So in this case, the 20 itself is the biggest factor they both have, or the greatest factor they both have in common. Okay, least common multiple, same thing. Build your factor trees and then ask your questions. What factors appear? 2s and 3s. Which one had the most 2s? The 6 did, and there was only 1. Which one had the most 3s? The 9 did, but there were 2. So I have to add another 3 in there and then multiply it all back together again. 2 times 3 times 3 gives me 18. So the first time they have a multiple in common is 18. And that makes sense. If you think about the multiples of 9, you have 9, 18, right? And for 6, you have 6, 12, and then obviously 18. So the list method would have actually worked really well there instead of making factor trees. Okay? Now we're going to look at the next question. Each face of a cube is a square with a side length of 8 centimeters. What is the total area of all the faces of the cube? Well, if we're dealing with squares, we need to square the number, right? So 8 squared is 64. But cubes have how many square faces on them? Well, if you think about rolling dice for Yahtzee, there are 6 sides on every dice. So I have to multiply my answer, 64, times 6. Okay, that means there's 384 centimeters squared worth of area on that dice. Okay. Now it asks us to write a power that has a value greater than 40, but less than 345. So I think the best way to do this kind of a question is to just throw some numbers out there. Let's think about square numbers real quick. Let's try 16 times 16. $256, not anywhere close to what we need. So what about 19 times 19? 9 times 9 is 81. 8, 17, 9, 1, 7, 6, 81. Okay, 261. That doesn't seem right. 19 times 19. 9 times 9 is 81. 9 times 1 is 9, plus 8 more is 17. Okay, still. All right, well, maybe try cubing some numbers. Let's think about the number 8. Maybe 8 cubed will get us there. Because 5 times 5 times 5 is 125. So it needs to be bigger than 5 times 5 times 5. 8 times 8 is 64. Times another 8 is, and this is called guessing and checking, literally. You have the whole hour to do your math test, so this is okay. 6 times 8 is 48 plus 3 more, 49, 50, 51. 8 times 4 is 32. 8 times 6 is 48, 49, 50, 51. That's too big. Okay, I'm going to do a little erasing. Well, I don't want to do erasing. I don't want you guys doing erasing, so let's not do that. All right, so let's try 7 times 7 times 7. Well, 7 times 7 is 49. And 49 times 7 is, I think it's 63. Boom. All right, this number fits right in between 340 and 345. Okay, so we can just do some guessing and checking on that. Okay. And again, if you're worried about not getting it and you're worried about time and you need a little coaching on that, that's fine. Just come up and ask some questions and I'll probably ask you questions in return to help you get through that. Okay, this one says a square vegetable garden has a side length of 8 feet. So if it's a square and it's 8 feet by 8 feet, the area is going to be of the whole garden 64 feet, right? That's why I put my 64 there. Okay, so the entire area of the entire square garden is 64 feet. You plant flowers in the center portion of the garden, which I don't know very many people who plant their gardens like this, but evidently this person does. And so inside the very center of that square garden, you have a 4 foot by 4 foot square as well. So the entire thing is 64. And the square inside is 16. So I need to find out what's left over. I have 48 feet left over. That means around here, all the way around here, right? And then I keep reading and I see that you divide the remaining space into 4 equal sections. So when you divide 48 by 4, you get 12 feet sections for the rest, okay? So your onions will go into one 12-foot section, zucchini in another, peppers in another, and tomatoes in the fourth. Okay, that should look very familiar. It's very similar to one of the questions we had on our quiz, okay, right after 1.2. Okay. The next question that we look at says, what is the greatest perfect square that is a factor of 147? That tells me if I do a factor tree for 147, I'm looking for numbers that repeat themselves twice. And in the factor tree for 147, I have 2 7s, don't I? And so 7 times 7 is 49. That means 49 is a factor of 147, and that would be our answer. So on this type of a question, definitely do your factor tree and then look for numbers that repeat themselves twice. Okay? This next one's kind of a humdinger. So let's just let me start with erasing what I did with the other group. I know it's dumb. I shouldn't even done this. Oh well. I'll just do it really quick. I'm sorry. It's just that some of it's covered up over there. All right. The first thing you read is you're filling piñatas for your friend's birthday party. You have 12 kazoos 18 mints, 24 lollipops, and you want all of your piñatas to be the same amount of gifts in each piñata with 0 leftovers. So what is the greatest number of piñatas you can fill? This tells me, since I have a limited number of things and I want to do the greatest amount possible, I need the greatest common factor. So I have 12 and 18 and 24. And if I'm looking for greatest common factor amongst those numbers, I can do factor trees. I love doing factor trees. I don't know if I've ever said that to you guys or not, but just so you know. And then with greatest common factor, we try to see what all they have in common. Each of them have to have at least one of it, right? They each all have at least 1 2. Okay, do they all have another 2 in the common? No. But do they all have at least 1 3? Yep. And so since they all have a 2 and a 3 at minimum, that means that we can fill 6 piñatas. Okay, and you can go further, like you can say in each piñata, they're going to have, well, for kazoos, 12 divided by 6 is 2. They'll have 2 kazoos. 18 divided by 6 is 3. They'll have 3 mints. 24 divided by 6 is 4. So they'll have 4 lollipops if you want to. Okay, but the biggest thing is here is this is an example of a greatest common factor question. And if you're worried and you don't know which kind of a question it is and you want a little bit of coaching, just come talk to me at my desk. I promise you I will give you a tiny bit of coaching. Here's an example of a least common multiple question. Stoplight A changes color every 45 seconds. B changes its color every 80 seconds. Both stoplights just changed 60 seconds ago. Okay, so after how many seconds will the stoplights change color at the same time again? Well, in this case, I need my least common multiple for those 2 numbers, the 2 numbers that are when those stoplights change, okay? And the least common multiple, again, to do least common multiple, you find your prime factorizations, and then you ask yourself those 2 questions that I made you copy into your notebooks. And those questions were, well, what prime factors appear? I see 2s, 3s, and 5s, okay? Then you ask the second question over and over again about 2, 3, and 5. Which prime factorization had the most 2s? Well, 80 did, and there were 4 of them. Which one had the most 3s? 45 did, and there were 2 of them. And which one had the most 5s? Well, they tied. They both only had 1. So then when I multiply all of that back together again, I got 720. And since the light just changed 60 seconds ago, that means I have to take away that 60 seconds to get my full answer, okay? And that's how I got my answer of 660 seconds, okay? And your question on your test will be almost the same as that, just have different numbers. All right. Finally, they talk about a tank in the shape of a cube. Please remember, if you see this type of a number, that means squared. If you see this type of a number with a 3 exponent, it means cubed. So if they're filling up a cubic tank with water, and each of the edges is 3 feet, that means we need to do 3 to the 3rd power. Okay? And 3 times 3 times 3 is 27 feet. That's my first answer, because then they ask you to find the number of cubic yards it's going to take. Well, if you know anything about measurement, you know that 1 yard has 3 feet in it. So all you had to do then was to take 27 divided by 3. Okay? I think it's 9, right? And then you would get 9 feet squared. Okay? 3 times 3 times 3 is 27. Yeah. Okay. I wonder if I can move that. Oh. Yeah. Wow, that's cool. I think that's right. Yeah. The answer key said 1 yard, 1 cubic yard for that. "27 feet squared." Three by 3 by 3. Oh. For every one set of 3 feet, it's 1 yard. And since it's cubic, then, interesting. This one, the answer in the book says 1 foot or 1 yard cubed. Okay, so I'm gonna have to play with that and come back. So the two answers are 27 feet cubed and 1 yard cubed. Oh. 9 times 9 times 9 equals 27.